All right. Yeah, I'll also upload the presentation to my website as well. I have the link to that at the end of as the last slide in the presentation. So grab a picture of that thing. Okay, let me see. Yeah, I usually I use a different laptop for my demos. I had basically a portable desktop, which I call, laptop thing. But my wife spilled water on the keyboard a couple of weeks ago and totally toasted it. So I had to get a brand new laptop, and I moved everything over here, but things aren't quite all necessarily fully set up. But I installed SQL Server and all that to get things going. So anyway, just some apologizing in advance for any technical issues that I might run into because of that. But yes, the fun stuff here. All right, so what I'm going to talk about today is indexing strategies to, determine, what sort of indexes you might need for either new database development or, modifying existing database. Just some strategies of how to go about the process. Plus in some cases I'll jump into some of the weeds on, B tree index structures and stuff, just so you understand better in the background what might be going on. I've given this presentation a couple of years ago here at the SQL Server user group, but I know we have some new members and, some folks might not have seen this yet.
So it's not showing slideshow, it's showing.
Oh, is something else showing on there?
The meeting has presenter mode.
Oh, right. Okay, hold on for a sec. So you're just seeing the whole presenter mode thing, not the actual.
The next slide.
Yeah. I guess I could just hide presenter view here just to get going. See it now? Okay. Skip through that. As with anything SQL Server, it depends. Indexing is probably the place where it probably depends most. There's so many choices, and every situation's a little bit different. It depends on your workload, the application. There's quite a bit. But at a high level, and it's best, in my opinion, to try to take indexing from a high level first, before you get into the weeds, but understand a little bit what we're trying to do with indexing. I'm mainly going to focus on, traditional, disk-based, B tree indexing, but I'll, just touch on some of the other index types as well during the presentation. But this is really the topics I'm going to speak to today. Including, a little bit of query tuning. The whole reason for having the optimal indexes really is to reduce costs, among other things. SQL Server licensing is expensive, so if you're running it on-prem, you need to have the appropriate hardware, and the most you can get out of that hardware on the same footprint is to your advantage. And indexes are really the key to doing that. To get the most compute out of, your database hardware. Also in the cloud, when you're paying for, your, compute costs, a little bit more directly, it's even more important because, the cloud compute costs can get very expensive, and especially when you're in the higher end service tiers and all that. So, indexing is the way you do that, because SQL, T-SQL is a declarative language. You're not telling, the SQL Server really how to do execute the queries, but it'll leverage any indexes that exist on the, tables and views to try to do the query as, quickly as possible, with the least amount of resources. And of course, there's other costs besides just the licensing and hardware and compute. And think about your end user productivity costs. If your system is snappy and responsive, for internal applications, or for external applications, the end user experience, if they're looking at spinners all the time because the database queries are slow or the application's slow, that's a bad thing. It really improves the experience of the end user when things are, run quickly. Um, a lot of times we don't think about it, but the indexes, in addition to improving performance, it also reduces blocking and deadlocking. And the reason is, SQL Server, at least the traditional, um, you know, pessimistic concurrency uses locking to guarantee data integrity while it, queries, data. And the side effect of that is, you can run into, long-term blocking, which slows things down, of course, and as well as deadlocks, which, require either retries or somehow the application handling those, neither of which are really, desirable. There's other ways to reduce blocking and deadlocks, and that's with, using optimistic concurrency, reversing isolation levels and those sorts of things. But even with that, indexing is really the first thing I suggest one, try to, avoid, any of those kind of concurrency issues, because in addition to, helping concurrency, it's also going to improve your, performance overall. And queries run faster and so forth. So, and the more headroom that your database server or your instance has, because you've paid a lot of attention to, query and index tuning, then the more scalable it'll be. You'll be able to do a lot more on less, and that's all good stuff from, the perspective of your organization. Now, indexing isn't the only thing. It also, depends on how your application is designed. I'm sure we've all probably seen dumb applications that execute the same query over and over and over and over again unnecessarily, when it would have been very easy just to cache the result, just execute the query once and hold on to it. In the case of, static data, like if you have a list of country codes or countries and cities and that kind of stuff, that's a perfect case where, the data could just be cached instead of having every single request or every time you load the web page, have it, have to, go and fetch the data. And it kind of goes without saying, but you have to have enough infrastructure to be able to satisfy your workload. You can't have, expect a small server or a small, VM or whatever to be able to satisfy, a really busy, application. A little bit of common sense and, comes into play here. But the whole purpose of B trees, what it does is it keeps logically related data close together, um, physically in the same pages, which has the side effect of reducing the logical reads required to bring the data into memory. Um, Keep in mind that even though a lot of times we might visualize SQL Server as a matter of fact, on the diagrams, we oftentimes have like a disk drive picturing your database and stuff. In reality, SQL Server operates on data in memory. That's the only place where it really works on data. The only reason we have the disk and storage is really just for long-term persistence of the data. So SQL Server always operates on the data in memory. So if you think about your indexing strategy to try to keep that data in memory and keep data that's closely related, or logically related, physically close together on the same data pages, it eliminates the need for SQL Server to have to go out to storage to retrieve the data, because it'll be in memory, most likely be in memory. So in other words, it helps improve the buffer efficiency. Um, Indexing with B trees, because they provide an ordered access to the data, it doesn't have to sort the data in order to provide an ordered result, for query optimization. So obviously, you'll need ordering if you have an order by clause in your query, but you also may need ordering for certain types of joins. Whether, for example, a merge join requires both results to be ordered in order to facilitate, processing that merge. So in addition to just avoiding sort operators, or otherwise you need to have a sort operator to provide that ordering that's needed for SQL Server to execute, plans that require ordering, in their operators. So this is really, a lot of this is a review. I know a lot of you already know about clustered indexes and non-clustered indexes, but I'll speak to it a little bit here just to make sure we're all on the same page. Really, in SQL Server, you can organize a table as a heap, which basically is a table with no clustered index. It's just a funny name for it. A B tree, which is a table with a clustered index. You can also have a column store index organized table, which is just having a clustered column store index on the table, which is not a B tree. And I'm not going to cover that today in this presentation, but I just want to be aware that it's out there. Column store indexes are most useful for workloads that require large scans, such as decision support, reporting, less so for, online, OLTP type workloads. And to a certain extent, they can help, reporting workloads. And for specialized use cases, you can have memory optimized indexes, which, as the name implied, are, actually not persisted on disk, but they're actually built and maintained in memory. In which case, when a table is organized as a memory optimized table, there is no clustered index because there's no need for one, because the actual memory addresses suffices the pointer, if you will, to individual rows in the table. And to that end, every row in a table has a unique row locator that SQL Server maintains, that its physical location, if you will, or it's the way that SQL Server actually gets to the row on the table. With a heap, it's basically the physical pointer, which is the file, page, and slot within the page that has the row. And I'm not going to really cover heaps today. I'm kind of an advocate that every table should have a clustered index, with rare exceptions. And those exceptions would be like for a staging table where, you just load the data once and read it once. But anytime you read data more than once, a lot of times you'll benefit by having an index to help locate the data more efficiently, rather than having to scan the whole table. Because if you don't have any indexes, the only thing that SQL Server can do to locate even a single row in the table is to actually do a full table scan, as you might imagine. The indexes are really just to help it, locate the data more efficiently. How it stores this is a little bit of a, into the weeds internally, but I think it is important to understand why we do some of the things we do. So that's why I'm going to cover some of that. The row locator, importantly, is stored, in the as it is. Well, the row locator is stored as the index to point to the individual row itself. It's also used for, as the for row level locking. It's used as the key when it computes the hash for that. We have a question.
We have really small tables. I have people all the time saying, it's a tiny table. It's not going to be refreshed or added to. It could be location table or state table, something like that. And they don't want to put a key or.
Yeah, so the question is, if we have a small table, do you need indexes? I'm of the camp where I think every table, if it can benefit, regardless of table size, if query predicate, something that's in a where and join clause, references the columns in that table, and it can promote a seek operator, then you should create indexes on that table. But even so, even if it's a one row table, that kind of stuff, it's a good idea to have indexes on specifically your primary key. In a relational database, every table should have a primary key, if it's a relational type table. There's some exceptions, like if you have a table that's nothing more than a log of, events or something, that it's not truly relational database. You're just using SQL Server storage engine. That would be an exception to that general rule. But, if you have a primary key, you already have a essentially unique index. And that index can make SQL Server smarter in generating execution plans, especially when you're joining to other tables. If it knows a given value is unique, it doesn't have to, or add things to the query plan for nested loops, etc. In other words, it doesn't have to do an iterative operation sometimes if it knows that the value is unique. So I would say that if you have any key columns, that those should probably be indexed and unique if possible. And I have a slide where I elaborate a little bit on those recommendations.
So similar to the same question, similar to the question you had, for tables that are active tables, so that you still have index, created index, and I think to be system generated on or
Yeah, so the corollary is that if you have a, I guess a denormalized aggregation type table is what, if I understood you correctly. Um, I guess I would ask, is that primary key, surrogate key in that case, used anywhere? If you ever have a table with a column that's a surrogate key and it's not used in any queries, it's not used in any joins, I think you have a red flag there. Either based on the data model, maybe you already have, your true primary key is even though you don't declare it as such, could be one or more composite key columns. In other words, a row in a relational table, if you go back to your data modeling, the data modeling didn't start with, hey, so start with primary key or surrogate keys, some arbitrary number or GUID that uniquely identify a row. It always starts with your actual logical model, your attributes, customer ID, state, zip code, all that stuff. And making a wide composite key sometimes gets, a little bit unwieldy. So that's when you deliberately introduce that surrogate key just to avoid having to join on many columns and index all those many columns. But that should be a conscious design decision, not one that's just, hey, let's throw an identity column in every table and say, hey, I'm a DBA, I know how to model data. It really requires thought, and every situation is a little different. And, there's always going to be some exceptions to that. So just again, I'm not really cover heaps in detail, but with heaps, there is no logical ordering of the data. It's wherever the data happen to be on disk and physically located. When SQL Server scans it, it just scans the data pages in allocation order, not any sort of logical order. With B-tree indexes, the pages are actually provided. There's logical ordering that occurs. And the way it does that, this is regardless of whether or not it's a clustered index or non-clustered indexes. The B tree is really similar in terms of its structure. Essentially, it's a hierarchy of rows. But starting at the data pages, any rows with contiguous keys are stored in the same page, with based on their comparison value. So, so they're all guaranteed to be, within the same data page. Within that page, the rows are ordered by key in a structure at the end of the page called a slot array, and that provides logical ordering. So when SQL Server reads a page of the leaf page of a clustered index, the slot array actually contains pointers to the rows within the page in logical order. It doesn't actually bother to order, like some people think that a SQL Server constantly sorts the clustered index or index keys. It doesn't need to sort it. It just maintains that logical order. And the rows inside the page itself might be out of order, but that's really just an implementation detail. The key is that SQL Server can read the page and read the rows in that page in order by key. So that's how SQL Server is able to do that, fairly, easily. Now, other pages are linked together in logical order by its key, with with having previous and next page pointers, in the chain, so that they're chained together logically. So it doesn't. So if you insert a row into a billion row table, it doesn't have to sort all billion rows, figure out where to stick the row and in there and do it. It just reads where the row belongs within the table based on the contiguous keys, and it will store the row in the right place. So the whole B-tree index essentially is a hierarchy of pages, starting from the root at the top and leaf at the very bottom of the hierarchy. And here's a little, any questions so far? I'm sorry, I didn't pause there. All right. Yeah, feel free to raise your hand or interrupt if needed. So this is a little animation of how the, index leaf pages. So this essentially, let's say this is I'll just say this is a clustered index for discussion purposes, even though the same considerations apply for non-clustered indexes in the B tree. You start with an empty page, and when you insert a row, This is the first to say this is an empty table. So it started by, just inserting it into the one and only page in the table, because SQL Server, the first time you insert data in a table, that's when it actually allocates a page for the table, and then it does its thing. So it inserts the row in there, which the key or the row. So each page has a page header at the beginning, and that slot array I mentioned at the end. And that slot array is what maintains the logical order. So when I insert these keys in the table, in addition to the row locator and the other data columns in those rows, it also maintains the slot array at the end of the page, and with the offset of each record. And in this animation here, I'm just inserting those in any arbitrary order. And even though the pages on inside, even though the rows inside of these pages, rows inside of the page are in an arbitrary order, the slot array has them in the correct logical order. So the very first key, key 1, is at the end of the slot array. Key 2, even though it's physically, I'm sorry, I haven't inserted key 2 yet. I'll say key 5, for example, even though it's physically in the middle of the page, the slot array has it in the proper order at the very end. So when I insert a new row, and this one here is key 2, we get what is known as a page split, which I'm sure you've all heard of. So it has to, because it has to store the contiguous keys in the same page, and that page is full, it needs to make room for the new row and store, data that's next to it, contiguous in the other page. So it takes half of the, rows roughly, and moves it to a new page. It puts the new row, in the page that are, with the contiguous keys. In this case here, the values 1, 2, 3, and 4 are in the first row, and then the remaining values 5 and above are in the second row. I'm sorry, second page. And then because we have more than one page now, it creates a doubly linked list, so that the lower the rows, basically ordering the pages in order by key. So the first page points to the second page, and the second page also has a pointer back to the first page, so that that index can be traversed in reverse order when needed for descending sequence and reverse sorts too. And when you have more than one page, it needs to have another another row in the another index level. In this case here is the root. There's always a root page. If there's more than one row in the table, and that. So if I need to read, key number 6, for example, as a random lookup by unique key, first thing it does, it looks in the root page, says, okay, that belongs in the second page here, because it's greater than it's greater than the lowest key there, and it knows which page to go after, and then quickly retrieves the data. And that process continues as the pages fill up and you add more and more rows to the table, more leaf rows. It has to create additional intermediate nodes, and then a root node. And larger tables will have multiple intermediate levels here. So you can have there's no practical limit to the number of rows you can have in the table, just limited by available storage nowadays for the most part. Any questions yet? Good. So again, going back to why we create the B tree, it provides equality lookups by unique key. Okay, if you read a row by a primary key or unique index, it's fairly efficient, because it just goes and traverses the index by reading the root. Whoops, I meant to stay there. By reading the root, then the one appropriate intermediate, and then and then the leaf row. So that's fairly quickly. And if I retrieve multiple rows by a non-unique key, it can essentially follow the the forward pointers to read the next pages in order, so that you can retrieve the additional rows as well. It can, and because it's already maintain those, it's maintained in logical order. So it can order the rows without sorting for query plan operators that need reorder, like the merge join and the stream aggregate, that kind of stuff, order by clause inquiries, and aggregation of rows without hashing when you have group bys and, partition by clauses. So I'll jump over to the management studio. Let's see. Of course, I got started a little bit late here, so I didn't have a chance to get everything prepared here. So let me make sure I'm starting fresh. Oops. Yeah, so for this, okay, so I restored the database. So I'm going to be using the, excuse me, what setup? I'll be using the AdventureWorks database later in the presentation, but for now, I'm just going to go ahead and start with the just a empty database here, demo database. So here I just create a empty database, nothing in it. Have a little utility proc just that I'm going to use just to dump some of the pages, just to show how the B-tree indexes are organized. Shoot, I go that far. Alrighty. Okay, so I'm going to create this empty database in this little demo table that just has nothing more than a column that I use as a primary key and some other data payload that I'm just going to put a bunch of values in there, and I have it structured so that it's easy to just eyeball it because I'm going to do a hex dump of the page itself, and you can't really make sense of it unless with your human eyes, unless you do it. So, remember that animation slide I had where I inserted 8 rows. These are those same 8 rows that I'm just going to insert in an arbitrary order. Let me get a little bit more real estate here. So I just like this is arbitrary order, key 1, key 4, etc. And that's a varchar column. So SQL Server is going to maintain that in order according to character, sorting rules. So now go ahead and just dump that data page. Here's the relational view of it. In other words, I have this is all the pages allocated to the table. It only has a single data page, and has 8 slots in it for, one for each of those 8 rows. And in the actual, let's see if you can see that better here. I'm trying, it's not. I get a little more real estate on that screen. Oh, there we go. Yeah. So in the one page, you can see in here just eyeballing it because I replicated the number 1, for Q1, and replicated 4 for Q2. You can see within the data page that all those rows are in that same as insertion order, but it's really an arbitrary order, and SQL Server will maintain that any way it chooses. But the end of the page has that slot array, and if we look at the end here, it says it's basically saying the first row in the page is at offset, 96, the second one at 1942, and so forth. But it's pointing, this is the logical order, which is correct, even though it's pointing to different places on the page, which might not necessarily be the same as the physical order. Now, if I insert that second row to cause that page split, same one that we saw in the animation, and do another dump, now we have and that root node, page level 1, this is the root node of the index plus 2 data pages, and the previous and next pointers are maintained on the data pages of the the previous and the next page, so it can follow the logical order both forward and backward. And even though there was a page split, something worth noting, the SQL Server still, this is the first page in the table, but it still has data from the before the split, because it doesn't it doesn't bother to clean up all the pages as it goes and make zero fill binaries, zeros with stuff that, are artifacts of data past. It doesn't bother to clean that up. That'll get cleaned up later as part of a Ghost cleanup process, or when you reorg the, index or whatever. But it doesn't have to, clean things up as it goes along, because performance-wise, there's no reason your end user should have to wait for all those cleanup processes just to insert a new row in the database. So SQL Server is optimized to defer that kind of work until later. This is the root node of the index, which is hard to read, but it just has the the pointers to the the other pages. Yeah, right. And I'll just insert a bunch more data here just to fill up the table with, like, I forget how many rows I put in there, but there's a lot of them. Like yeah, dumped it. Okay, yeah. Now because I have more rows in the table, we have that, we still have the root index, but we have two intermediate rows or pages for the intermediate, because we have so many data pages now because of the additional data. But the rows are actually on, in the table. If I, run a query where I order by it, and I also show the physical locations, this is the, the order by logical key. Um, these are those first, 8 rows or 9 rows that I inserted. And this is that bulk, insert I just did, where the values are a little different. But, as far as the, when I order it by the clustered index, which has these key values, 10, 11, etc., we see that that's, different than, the other, there's a non-index column called other data right now on there. Now, if I create a non-clustered index on that table too, and I repeat that same, query just to dump the pages, here I'm just dumping the, the non-clustered index, showing you there. So that'll, we have essentially two levels to this index as well, but the the root node or the leaf nodes of the non-clustered index are not the data pages. It's really just the index page that has the key of the clustered index to use as the row locator. So whenever I use the non-clustered index, it'll read down to the leaf node here, and then it'll do another essentially another seek for the clustered index to get the actual data values. Now here, if I do the same thing, this time I'm ordering it by the non-clustered index. Um, we see that the other data, which sorts differently because I didn't have that word key in front of it, we see that the later inserted rows, or when I retrieve in logic order, they're actually retrieved earlier. It doesn't matter what the physical location is. The physical location is totally different. But at the end of the table is where we actually have or I'm sorry, when I retrieve it in a logical sequence by the other key, is where all the other data is. Those newly, is where the original rows were inserted. Oops. Any questions thus far? All right, I'll talk a little bit, just mention the BW tree, which is it's basically a B tree structure that's specialized for memory optimized tables. With memory optimized tables, you can only have non-clustered indexes, because the memory address is, suffices as an efficient way to locate the data. One of the reasons SQL Server likes to use the clustered index instead of the physical file page slot locator in non-clustered indexes is because otherwise, every time a row location changed on disk, it would have to update that same pointer in every one of the non-clustered indexes. But in the case of the using the clustered index as the row locator, SQL Server, because that's relatively constant unless you update the clustered index key, it doesn't have to bother to touch the row locators in any of the non-clustered indexes. So updating or inserting or deleting a row, it doesn't have to, or should I say, if the row moves on disk due to updates and inserts, it doesn't have to do that extra maintenance overhead to maintain all those other non-clustered indexes. But anyway, with memory optimized tables, you don't need things that are kind of not needed for included columns either, because memory optimized indexes inherently are covering, since there's always going to be a memory pointer. And there's no provision for filters on a memory optimized table. Yeah, and the B-tree indexes for a memory optimized table essentially are created at startup, but they're really efficient singleton equality lookups, and they you can do multi-road retrieval with partial key just like you can with or full or partial just like you can with disk-based tables. But again, they're built on the fly. So a hash index, again, is also memory only for memory optimized tables. You're only, and just like any memory optimized index, you can only have non-clustered, excuse me. And with that, the unlike a B-tree index, because these hash indexes are not ordered in memory, they're just they don't have a B-tree structure. SQL Server just calculates the hash according to the key columns, and then can use that to locate the data in memory much faster. But again, I'm not going to have time to really discuss those in detail anyway. But they're very efficient for certain workloads where you're doing singleton and quality lookups. You don't need any sort of ordering, and all that, and you don't need any partial key lookups either. But they are very efficient, for workloads where you don't need to have that ordering. So I kind of touched on this earlier when I mentioned that it's always best to start with a relational table in third normal form. You kind of, and the reason is you already kind of get some free indexes, namely your primary key. You're always going to have a unique index on your primary key, like it or not. There's no way around it. SQL Server does that, for you. Same thing with unique constraints that you probably want on your table for data integrity reasons. But you get a free index with that, free in air quotes, meaning that there's obviously maintenance overhead and stuff, but you don't have to go through the conscious design effort of creating one. You kind of get a free B-tree index for that, But it is important to use the same data type for the same attribute. Don't have a customer ID that's in one column and varchar, and I'm sorry, in one table and varchar on another one, and big int in the third. If you're consistent, then SQL Server will be able to use the indexes more efficiently because you don't have to worry about the issue with it not being sargable, meaning that SQL Server doesn't have to convert from one data type to another during the query, because conversions can cause the index not to be used. So you want to make sure that at least the best you can that the indexes are used. So besides the primary key and unique constraint indexes, this is where you want to investigate where you're kind of think about where you may want additional indexes. Essentially, it's on columns that are referenced in where clause, join predicates. because those are where SQL Server can help, where clause will to locate the data, and the same thing with the join clause. The group partition by, clauses, it'll help, improve the query plan quality by leveraging things like, aggregates, when it's able to, for like group by and things like that, as well as the order by stuff. Some people say that you should always add an index on foreign key columns. Um, I think that it's oftentimes a good practice, but not always. It just depends on your workload and queries. An example would be, let's say you have a order table, and one of those columns is your order status. So you have an order header table, you have an order status, and that order status would be either new, I don't know, in progress, closed, whatever. And even though you might have a domain table for your order status, and you can, you can have a foreign key from your order header table to your order status table, and that that you may or may not actually join on that table. But whether or not you need to have an index on the foreign key column in your order table kind of just depends on your workload, because sometimes that index may never be used, especially if you're always looking for your, your orders that are in a specific, state. But uh, if your primary access point is by customer ID or something, then you might not find that the index is really going to be used. So you're going to have to look at your workload and your execution plans to see if it's really beneficial to have indexes on your foreign key columns, knowing that the only time that index would really be used is if you delete an order status, where it would have to look to see if there's any you know orders with that status already there, like but usually you don't, that's usually pretty static data. And then let's see, say specialized index, meaning covering indexes and filtered index and filtered views. I usually recommend that you don't do the premature optimization trap. In other words, don't jump to implement those kind of indexes right off the bat, but rather once your application is mature enough that the queries that are being run and the ones that are expensive, that's where you'll jump. It makes most sense to look into filtering and covering indexes. If you've ever done like the index, the database tuning advisor, chances are you've seen it with recommendation and you're missing indexes as well in your DMVs. A lot of times you see a recommendation for a bazillion included columns, and more often than not, that's overkill. And especially when you have many recommendations that differ only in one or two of the columns that are included, really have to take some of those recommendations and suggest, or I like to call missing index suggestions, with a grain of salt. But don't go overboard on implementing them. But if you have those critical queries, definitely these are things that you want to take a closer look at and consider. Making sure that they're covering it all. Queries that are I mentioned frequently executed because not all queries are created equal. And if you have a query that is executed constantly, those are obviously that are going to contribute to your overall utilization for your compute and everything. You want to try to optimize those queries as well as you can. And that's where you want to take a special look at the covering and filtered indexes and all. Any questions? You want to pay attention to the tables that are going to basically grow large, especially because those are I like to say death by 1,000 cuts, or just over time. It just you don't even notice it that your database or queries get slower and slower over time, and it's only because the cost of I/O is usually going to manifest, or having access data from storage is usually only going to manifest itself once your table doesn't fit in memory anymore. If your database is small enough to fit in memory, um, you're in a good place, because then once the cache is warmed up, it's always going to be in memory. And really the purpose of the B-tree indexes and, are to, reduce your compute costs and therefore improve your scalability, even though no IO is actually going to have to occur, once the cache is, warmed up. But don't pay attention, don't, only pay attention to your big tables. But the big tables tend to be unforgiving because, the queries run much longer when it has to do with scan. There's going to be much more likelihood for blocking and deadlocking and those sorts of things. So that's why, we want to pay attention to them. But the same practices you need to follow in smaller tables too.
Display.
Oh, did I do that again? I wasn't sure. Oh, no. Thanks, Julie. Partitioning is by the way, is great for manageability of large tables, and definitely something that if you don't already use it, you should take a look at it. But it does have a lot of restrictions, and there's a different paradigm. But that's not going to help your indexing, not going to really change your index strategy that much, aside from the fact that you may want to consider having your partitioning column, part of your or as the first column in a lot of the indexes. It'll help uh, uh, help improve sortability and performance, even if the table's partitioned. And I always recommend that pay a lot of attention to use quoted identifiers on and ANSI nulls on when you create your procs, triggers, etc., because that's a sticky setting that if you don't have those set properly, later on, if you try to create a filtered index or a or an index on a view, SQL Server will complain because it requires those options to be on in order to modify the index that's associated with that table. So just there's no reason not to. It's really these are legacy settings that stem back from legacy Sybase days from the 1980s and 90s. So don't just keep them on all the time. Otherwise what happens is you create a filtered index and then a proc, blows chunks because it doesn't have the setting right. Yes.
There's an online question. Are there any appreciable differences in performance when a foreign key column is listed first on the index versus second?
So the question is there, does the specification of the key order matter for the foreign key columns? First, it doesn't matter if the foreign key column is first or second. So I would need a concrete example there if you can think of one. I mean, to do, and I do cover that, I do mention it a little bit there here. It depends on your predicate. That's going to really be an equality predicate for all practical purpose. So when you have your the foreign key columns, I would say the general considerations apply, where if it's not just for the foreign key, but also being used for other purposes like joins and an aware clause, and usually you do join on your foreign key columns, you would specify the equality predicates first on your joins because and also the most selective keys as well first, in that order. And if you have other range predicates like a date column or something that you'll always search for where it's greater than that value or between these values and all, those would be last in your list of your keys. So I don't think there's any special consideration if that index is used as on a foreign key, and they're on the related table, that is. Yeah. Okay, and as with anything, there's always going to be a couple of exceptions to the general rules here. If you have a one-to-many join on a partial key, you want to specify the join columns first. And and I have an example in the demo that'll be coming up here, um, where essentially, let's see, how do I say that? Yeah, I'll defer that until answer that till the demo. If you have a single index that's used by different queries, and you don't want to, specify all the key columns, you want to specify the partial key columns, first, meaning that, try to remember how to. I had a lot of trouble formulating this statement, so my apologies here. Right, it's been a while since I looked at it here. Um, yeah. So in other words, if you have queries where on query one you have you join in columns A and B. In query two you have A and C, and you have an index on A, B, and C, kind of thing. You want to make sure that you have the A column first in the query, the columns that are common to all of your queries. Okay, I already ding creating a circuit key. Spoke to that already. Most, but not always, it's a good idea to make your primary key index clustered, but again, that goes back to the it depends thing. There's definitely cases where it's not best choice, but it's going to depend on your queries and the workload. So be really mindful about it. Don't feel forced into making your primary key the clustered index.
Yeah.
Yeah.
You mentioned the thing about date, in the order of the keys. The dates have to be the last. Normally, from the other orders, when you mentioned it looked like this, the number of key on the joins itself matters to make a faster join. For instance, what is it called? It's not sergeant forgot the term for it, but it's the number of unique values for that item.
Cardinality, I think. Yeah.
So if it has lower cardinality, then I normally have it on the left of my join predicate itself. Or the key column, it'll be the first, and also when I'm joining it, it'll be the leftmost. In the case of dates too, I would expect the same, but you mentioned dates would be the last. Is there any reason why that's the case?
Right. I use data as an example, the data type, but technically it's the question of whether or not it's an equality predicate. In other words, you're comparing for two columns to be equal versus with SQL Server, they call it inequality predicates. And that could, besides the not equal operator, which usually indexes don't help you a whole lot on, but the range predicates, like on where something's greater than some value and less than another value, that's where I use date as an example, because that's the most common use case that I run into for those equality predicates. And typically you would want those as the last columns in your key. If you're, for example, if your where clauses where, customer ID is equal to this, and the order date is between, last month and today or something like that, your column order you would want that to be, your customer ID followed by your date, not the other way around. Because otherwise, in order to do the order, scan, it would have to look at all of the orders in that date range for all of your customers, you know what I'm saying? And then throw away the ones that don't match the customer ID. So the index isn't going to be as useful as you might think. But you reverse the order such that your customer ID is first, and then your order date is second. Then you've already boxed yourself into just having orders for that customer, and then within that customer, you're only getting those orders for that date range. So when you run the query, when you think about it, you're only going to touch those rows that you actually need for the query. And if I had to distill this entire presentation down into one statement, that's really the strategy. The strategy is to only touch the data that you need for a given query. If you're touching other rows and throwing them away or doing a scan, then you're wasting those resources. And a lot of times this isn't really, it's not too well known, but when you do a primary key or unique constraint, there's no syntax to support the fancy stuff like the included columns or even filtered indexes for that matter. Um, but what you can do is create a unique index, because foreign keys can reference a unique index or a unique constraint, not just a primary key constraint. So if you have a primary key and you have a workload that needs to have some included column, if it's a non-clustered primary key, then you can create a unique index instead and use the include clause to include those additional columns, and then have the foreign key reference those same columns, but it'll be able to use the include columns to avoid the extra, key lookup for the clustered index as well.
Does it figure out itself if the index target is uniqueness or not, or how does it enforce it?
So the question is, does the let's see, does it figure it out? No, I mean,
They're having it unique.
right.
Because you might know that the logic ends up being unique indexing. I mean, obviously, if you're indexing somebody else's key, it can be logically derived that it's unique.
Yeah. So if you use the keyword unique when you create the non-clustered index, that's going to serve as this primary key, with an included column. That unique keyword will guarantee that the values in that table, aka the index, exactly, the keyword unique will guarantee it'll be enforced.
Index will force you to be unique on the columns as well.
Right, on all the key columns that you list, the set of the key columns.
Yeah, it'll create a new.
Exactly. Exactly. It'll guarantee that there's no way that you can have a dupe in the table, with that, just like a unique constraint, unique index, or primary key. Those are the three ways to have SQL Server enforce you can't have dupes. And the nice thing about using the unique index syntax is just that it gives you some little extra options on being able to, fine tune with an included column, some of your queries. All right, I'm going to jump over to Management Studio again and get back to AdventureWorks here. Let's see. I just had to remember I already restored the AdventureWorks to the way it was before. So, okay, yeah. So here I'm just going to run a query just to list all the queries in the AdventureWorks index. On my demo, I'm going to just focus on the orders tables. But just like if I'm sure all of you inherited a database at some time in your career, and you have no idea what it or the original DBAs or developers, they may have used a lot of different techniques of how they did their indexing strategy. In this case here, there's obviously a bunch of different indexes, and again, I'll just focus on the orders schema, or sales, I should say. So in the sales order detail table, which is the table that has one line for every line item on the order, it looks like we have a non-clustered index on product ID alone. We have a row grid index, unique index on it. And the clustered index is a composite index on the sales order ID and the sales order ID and the sales order detail ID. And they also have the sales order header table. They have several indexes on this guy too. with the primary key being the sales order ID, I think. Yeah. Which is identity column. So when you add an order, you add the header order as well as, one row in the detail table, per order. But since these rows in the detail table, the data modeler here decided that they want to have a composite key on the sales order ID, which is, the foreign key to the sales order header table, plus a surrogate key that they put on the sales order detail table, that identity column, because that way all of the orders for a given sales order are going to be essentially contiguous and within the same page as for a given sales order. So you do one logical reads and you're going to get all the order or many orders for that customer. So that's why they chose to do this, which is, I don't like to use the AdventureWorks database as the poster child for here's how you model databases, but this is really a good pattern though, in the sense that they use a composite key instead of just having a standalone key on sales order ID as the sales order ID primary key and a separate, as a standard, as a separate primary key. They actually chose to use a primary key to facilitate the join between your sales order header table and your sales order detail table. So it's able to access the rows in this page within, in order, which is a good approach to take. All right, let me jump over to the next one. All right, so for the purpose of this demo, think about, you inherited a new data or an existing database, and you have an app. There's a AdventureWorks, and there's an e-commerce site, the front end, public facing for your, people to order stuff from your company. And to that end, anytime a customer logs onto your website, when they sign in, they get to see all their 10 most recent orders or the recent orders. So to do that, we have a stored procedure where it takes the customer ID and returns a paginated result set of the most recent orders. So essentially it's just grabbing, for this one customer from the sales order header, it joins on customer ID and it does an order by the order date descending, because the customers want to see their most recent orders, which is, by order date. And then the application, just by configuration, let's say it has 10 rows at a time on their page, but the client could, scroll through that as needed. So if I create that, I don't know if I ran that or not. Anyway. So I'll create that stored procedure. That's not out of the box with AdventureWorks. And if I run this query, the only columns I'm grabbing here is really just sales order ID from the header table, order date, and ship date. And then it just has it uses a case expression just to figure out what the order status is. So when I run that proc for a given customer, I see his most recent orders. Obviously, nobody's ordered stuff in AdventureWorks for about a decade or so. But, these are the 10 most recent orders. Let me show the actual execution plan here. So all this, so the only table this proc is currently touching is just the sales order header. I'm not sure only table it's using is the sales order header table. And to get each one of those, it does the index seek based on the customer ID. And for every row returned, it does a key lookup to grab the additional columns that are not in the that non-clustered index, in other words, other columns of the query. And then it goes through, it grabs all the orders for the customer. Then it has to sort it down by date in order to satisfy that order by descending clause. And then of those, it just it just returns the top 10 because of the top clause. So all that being said, when it runs it, and I ran that with statistics IO on, you can see on the sales order table, I had to do 38 logical reads to, do all those key lookups and grab all the orders for that table. So what I'm going to do here is start a PowerShell script that just runs a query like this, runs this basically the same query for every customer in the database, and then just iterates over that list of customers in parallel to simulate what would happen. Hey, if I had my website and I have 100 customers logged in, they're logging in and they're jumping around, that's basically what it would look like. So I'll run that PowerShell script here. And I'll also pull up Performance Monitor just so you can see the resource utilization before we make any other changes here.
And I apologize for anything, but mine has been taken up.
Oh, it's bad.
Really bad. My paper is home.
Oh, no.
I apologize.
Oh, absolutely. Well, good luck. Yeah, so right now I have that script running that, like I said, it's just executing that same proc with different customer IDs, pretty much just over and over again, just iterating over through the whole list. Very good. So, so I have PMON and the counters. This might be a little bit hard for you to read in the back here. But so the highlighted counter that I have right now is the batch request per second, which is a measure of how many queries per second, how many times that proc is getting executed right now. So on this notebook laptop right now, it's executing at about a rate of about 30,000 or so executions per second with the different customers and different orders and all. And it's pretty much, let's see, about half the time is used by SQL Server CPU time, and the other half is used by my PowerShell script because it has to do the work. It's a client application that's, reading the rows and, consuming the results. But as is right now, like I said, it's doing about 30,000 queries per second. CPU overall, and I should probably add the overall CPU on my machine, but it's my CPU is running 100% right now because between SQL Server and that PowerShell script, not counting PowerPoint, it's using all the it's using all those resources, all available compute. Let's see if I can find that here. Yeah. Okay. Processor only says 50% right now. I'm not sure why. Either way, it doesn't matter. So if we looked at that execution plan, as you may remember, we had that, I had to do that sort, to do that descending key sequence thing. So what I'm going to do is just rebuild that existing index, that they already had an index ID on, on customer ID. Here I'm essentially adding order date is the second column to that index. So if I do that, and take a look at the execution plan. Now, when I execute the proc to get all the orders from a given customer, it does the index seek just like it did before and the nested lookup, nested loops. But as you can see, there's no order by in here anymore because it's able to actually, even with the top clause, it's able to do the seek on just the customer ID. And this is going to be ordering it, it's doing an ordered scan, for just the orders for that customer, in for that key lookup. If I go back to my, PMON, whereas before, it was averaging around 30,000 executions per second. Now with that, adding that extra column, it's closer to 40-ish. It's a bit higher, maybe about 5 to 10,000 executions per second higher than it was before, just by eliminating that sort operator. Um, um, and then, but it still has to do that key lookup. So what I'm going to do is just another iteration here. I'm going to go ahead and add the ship date, which is and status, which is the only two columns that are two additional columns that are not in the index that query needs. Just to see, how that affects the execution plan and performance. Now, when I look at the execution plan here, as you might guess, we don't have that key lookup anymore. All we have is a index seek, and already had the scalar and then in the top clause. So that looks a lot simpler of a plan and more efficient. And it looks like it is, just looking at the current execution. As you can see, it's gone up to a little over 40 there. Yeah, right now, peaking about 47 is what I saw. But as you can see, the number of page lookups per second, measure of the logical I/O, it dropped pretty significantly. Once we eliminated that that key lookup too. So essentially, this is just an example of an iterative process where you have a critical query that's executed. I mean, there's nothing more critical than on the customer's homepage from a customer perspective, and it's executed very often because we're a successful company and a lot of people use our website. So it's able to like, again, this is on a notebook laptop, and it's able to do on this notebook, it's able to do 40,000 executions per second or so. And let's say our business folks like to make things hard on us. So instead of having that be good enough, they also want to on that same web page, they want to show how many items there are per order on the grid. So what we did is we had to add another column. This time, essentially, it's just using a subquery to join to the sales order detail table just to get a count of the number of orders, per just to get a count of the number of orders, or I'm sorry, number of items for each order. So this is a new version of that proc, but because now I'm hitting the sales order detail table, it's a lot more expensive. So so the throughput dropped a bit. So now it's back into 30,000s per second again. From when it was before, it was up around 40-ish, and the page lookups has gone back up. So just as an attempt to it's just by its nature, it's going to be a more expensive query, and there's not a whole lot of magic I can do there to help. Looking at the execution plan, though, we have the same index seek, but it also, for each one, it has to do a stream aggregate, a cluster index seek plus the stream aggregate to get the the count of the number of items per order, because we already had an existing index to help facilitate that, so it wasn't that big of a deal. But just to pull out all the stops, let's say Cyber Monday's coming up and your website is going to get really super busy. If I create a index view on top of that, to materialize that count, let's see, I haven't looked at that execution plan. Hopefully it'll be a bit more efficient this time around. Yeah, so it does an index seek, and then it does it automatically, even without changing. I'm not even referencing the view in the query, because I'm running on this laptop or notebook, I'm running, developer edition, and it can use the index views even though you don't directly reference them in queries. If I was using standard edition, it would be mandatory to I'm sorry, you'd have to do no expand hint in order to use that index view. but the execution plan looks a little better. But in practice, I really don't see any, any major difference in the resource utilization or throughput. So it might not be really worth it to go through those, extra hoops, for this particular, workload. But it is something to keep in mind on your back pocket is like a, is, the, excuse me, is, indexes on views. And also with, you can try, if you're with the small database that will fit in memory, even on my laptop, I don't really have to worry about page compression or row compression, but those are other index options that are good idea to consider because it allow more data to fit into memory. Therefore, you won't have to do as much IO. And even with the extra compute costs, you can end up, improving, overall, performance. It's something that's going to be dependent on your, specific environment and workload. Yeah, so here I just changed all the indexes to page compression, and I'm getting about the same level of CPU utilization and throughput still, even with all that compression. But if this was if this was a terabyte database or something, then you would see you would be able to get a lot more data in memory, just with those compression options. So those are other index options that are, a good idea to consider. And I even tried page compression before. I don't think I saw any difference there either. Okay, yeah, now, yeah, there's jumped up. Yeah, so now it's roughly about the same. So any questions? Yeah.
We have some queries that when the indexes get fragmented, they get pretty slow and they speed up right away when we do a re-index all. Only if though we add the update statistics qualifier on the re-index. So what's the statistics qualifier do? Re-index.
So what kind of so when you rebuild the index, what kind of,
Yeah, I think they're not clustered indexes.
okay. So you have a non-clustered index, and did you rebuild it with an alter index rebuild or?
Yes. But then the only thing that speeds up the performance is if we have that statistics qualifier on the re-index.
Statistics qualifier.
Statistics on, I think it is.
Boy, that's not ringing a bell here.
You said something.
In general, if we're going to create a unique index, should we create it in the context of creating a unique constraint, or as a general principle, understanding that it could depend on the workload of which we're creating the index for? A unique index. Yeah. Okay. Okay, thanks. I'm asking. Thanks for coming. I don't hear him. I don't hear him anymore. Can,
Okay, how's this? Better? All right. Teams challenge here. Try this again.
So you were discussing, index maintenance.
Yeah, so yeah, just to close that answer, yeah. So my opinion is as long as statistics are up to date, the only advantage to reorging occasionally is just it'll get rid of the unused space within the data pages and do that cleanup like we saw earlier where there's a bunch of garbage in the due to artifacts of previous page splits and stuff. So it'll improve your buffer efficiency, but it's something that you don't have to go out of your way for unless you're pretty constrained on your hardware and your workload. In other words, I wouldn't bother to do that every night type thing.
If you have something really big that's maybe not going to be fitting in your memory, as it gets fragmented, split.
Right. So the question about larger tables, the same considerations apply, though. It's really helping your buffer efficiency. You know, in other words, you're going to have a lot more rows in memory at a given time, even though it's going to be a fraction of what your entire table is. Requesting those rows won't require an IO because it's already there, type thing. But exactly how often, kind of depends on, your workload. I personally, um, you know, like to have like a weekly process or a monthly process to take care of a lot of that kind of stuff, just using a whole lot of scripts, based on some of those thresholds. But I wouldn't, uh, I think that a lot of DBAs are way too aggressive on reordering just to avoid fragmentation because you really don't get the kind of bang for your buck on the more modern storage systems where, your SAN or SSD almost rivals memory access in terms of performance. Not quite as fast, but especially on local SSD. And there was another, was there, that previous question, did I fully?
I think so. He's jumped off, but I think that was.
Okay.
Quick one. So if you take backup and you push it down to a dev environment, what kind of cleanup or thing working? You just rerun it under indexes when you push it.
About, yeah.
Backup and restore it down.
Yeah, well, to be honest with you, for the last decade or so, that's been a no-no for the companies I've worked with. So yeah, I hear you. Listen, welcome to the real world, but in addition to normal data scrubbing, getting rid of any sort of PI or MPI type data, um, I haven't, back in the day, I didn't really bother aside from let the regular maintenance kick in because I still would run the regular maintenance in dev, just like I would production, you know. Any other questions? Okay, well, I'm running over, so I'm just going to blow through the remainder of these slides, just as talking points for some of these index options that I've discussed on and off throughout the presentation. I can. Where was I? Okay. Most of this stuff I've kind of mentioned at one time or another already, so I'll try not to belabor it too much. So you have up to 999 non-clustered indexes per table, which is way too many. Nobody should ever come anywhere near that in practice. But back in the day, it used to be like 16 indexes, and it keeps upping every new version and stuff. Yeah, so this is really just about what I think. I got two of these presentations open here. Sorry, I had two of those open. I have to get back in here. Ah, shit. All right, so these are just, so I didn't really speak about the ascending, descending options for each key column. But if you have an order by clauses, excuse me, um, as long as you're only accessing all the columns in ascending or descending sequence, then you don't have to bother with having a special ascending or descending specification when you create the index. The exception would be if you're mixing and matching ascending and descending for the same index keys. And I'm trying to think a good example of that. But if you have a what you call it? If you're ordering by, I'll say, customer ID ascending and then date descending, and you have a single index on customer ID and date, then you would want to specify descending if it's a situation where you're accessing multiple customers at the same time. So the demo I had where Adventure worked, it was only one customer at a time, so it didn't really apply. But that would be a case where you'd want to specify ascending or descending, since SQL Server only maintains one forward and backward pointer. So you can only have one direction for the index, one or the other. You can't have a mix of ascending and descending in the same. Where SQL Server needs to have that extra index there. Let's try to think if there's any other thing else here, talking point wise. Yeah, I mentioned a little bit to make sure that you always have your magic 7 settings on, particularly the quote identifiers and ANSI nulls. That also helps avoid plan cache float too. When you can have multiple execution plans that differ only by set option. Yeah, okay, I spoke to that a little bit already. Yeah, you may see the optimize for sequential key option for incremental keys, but I just want to uh, I just want to mention that's really only for really extreme high volume inserts type scenarios. Typically, I would not even bother with that. And here's a link to the reason why, the scenarios where it might help. Let's see, so regarding just incremental keys, which is to say, if you have a circuit key like an identity or a sequence, a new sequential GUID, et cetera, it does have both advantages and disadvantages. The advantages being that it reduces the fragmentation and improves your buffer efficiency, but it can cause, page lag IO contention at very high insert rate scenarios. I'm talking, generally thousands of inserts per second at that rate. So, you just have to watch out for that. Random keys are good in the sense that they avoid the page latch convention, but it also greatly reduces buffer efficiency. And for that reason, just it's better usually to have incremental keys when it comes to surrogate keys. I think I spoke to most of that stuff. So. All right. Yeah, just make sure that you're to use the indexes efficiently, make sure you have sargable expressions, meaning you don't want to apply functions to the column in the where clause. And, pay attention to your data types, make sure that they match. here's a example, like you don't want to say we're year of order date to get orders for this year. You wouldn't want to say we're year order day is equal to some, year. You'd rather do it as a range predicate with generally with an exclusive, inclusive begin date and an exclusive end date so that it can actually use the index efficiently. Because otherwise, the SQL Server would have to read the value of the date to figure out what the year is and won't be able to use the index without scanning the whole index. And this is a biggie if you have, especially on the application code where they don't properly parameterize queries or whatever, where they accidentally use Unicode parameters when instead of regular varchar parameters. So if you have, if you see an index is not being used by the application, make sure that they're using parameterized queries that are using that they don't use Unicode when they mean to have a varchar, because a lot of languages default to Unicode nowadays. So gotta watch out for that, dude. Yeah. So in summary, just a matter of fact of, touch only the data that you need and try to be proactive on the execution plans before, you go live in production. And you can do some query tuning like, the Sargwell expressions that I mentioned and all to make sure that they can be used efficiently. And, the DMVs like the unused indexes and, they also expose the possible missing indexes and, you can, review those for some clues on where to look to help, tune your workload. And I'll upload the presentation, this evening to website there. So you can download. I haven't put it up there yet, so don't bother to do it till tomorrow. So if you want to take a picture of that, if you want to download later, but it does have all the script in it as well as the slide. So it should be everything you need to know about indexing strategies. Any other questions before we wrap it up for today? Talk about fun stuff.
Well, now I want, I think this is where it's supposed to be.
Got a pretty out there question. You ever work with a client that uses something like Tableau or Power BI and they don't do live querying, they only use data imports? So have you seen an indexing strategy making an impact on that sort of scenario? Like once the data is imported into the application, Power BI or Tableau, the fact that it's already been indexed, does that have any impact?
If I'm understanding correctly, so I thought that, for example, Tableau and they could hit the data source directly. Are you saying that there's a separate data mart, or is this something that's imported in the tool itself? Either or both?
Data may be, it's not going to utilize the indexes that are on the data at the original source. And I don't recall anything going, I've not seen any indexes get applied to data that has been imported. I can't speak to Tableau for Power BI. I've never seen it indexed once it's supposed to do the work. So the query strategy is applied, but is it true index? I've never seen that in Power BI. And I think that's probably due to the data size limitation of the data within inside that's supposed to be inside of Power BI. The idea being that it should already be